Okay, so in this week we will solve some questions in this week 2 problem solving live session, and these questions will definitely help you in solving the week 2 assignment for the analog electronic circuits course on NPTEL. So let us start. So these questions are similar to your assignment but not exactly same. Some values are different and some concepts may be different somewhere. So please pay attention when you attempt your assignments. So this is the first question. Here we have been given a PMOS. This is a PMOS. And what has been asked is we have to find the current, small signal current ID. And we know that K is 28 millisiemens per volt. So what is the equation saturation? ID equals to K VGS minus VTH whole square, right? And here they have taken minus because they have taken some sign convention, that is the current going into the drain is positive. That means they have taken this direction ID to be positive, but current will actually flow like this, right? So it therefore here it is negative. So let us solve this question. So this is the diagram. I have just drawn it here, and if you see from the videos, this is the equation of the small signal current, and you must have seen it in the video. And if you have not, I recommend you to see those lectures first. And what we know that is del ID by del VGS is nothing but the transconductance GM, and del ID by del VDS is the output conductance GD, right? Is there a problem in these two? Like how, from where these current equations are coming? Please open your mic and speak if there is any doubt, okay? Okay. So what is our next step is, okay. So here, uh, yeah. So since we have been not given anything about the trans output conductance, and it is generally very small compared to the transconductance. GM is much greater than GD. We can assume this term to be approximately 0. So then ID would be just become ID equal to GM VDS, right? And then if you know what is GM I have just written, it is, this is GM, right? GM is del ID by del VSG. I'm writing VSG because it is a PMOS. If it was an NMOS, I would be writing VGS, right? I hope you know this. And it is nothing, just the derivative of ID, so it will be minus. Okay, let me just write ID first. What is ID? ID equals to K VSG minus VS minus VTH whole square, right? Del ID by del VSG. This is GN, transconductance, equals to 2K. Okay, it was minus, right? Minus 2K VSG minus VT. So now we will just substitute the values. It is minus 2 and K is given 28 millisiemens. 28 millisiemens per volt. VSG, let us calculate VSG first. So this is source. and this is gate, right? And we have been given Vx is 1.9 volts. Vx is 1.9 volts. So Vs minus Vg, Vsg equals to 3.3 minus 1.9. That is equals to, okay, let it be 3.3 minus 1.9. So 3.3 minus 1.9. This Vt is given to be threshold voltage is 0.9 volts. 0.9. So we will get Gm equals to approximately 28 millisiemens. Okay. Now this was our ID, right? Okay. I will written it wrong. ESG ID equals to Gm VSG. Small. This is small VSG. That is the small signal, right? So and it is given the small signal V is applied. Vx equal to 4 millivolts of small signal is applied, right? So that is they are saying that 4 millivolts of small signals is applied here, and we have VSG. So it will this is it is applied to the gate terminal, not the source. So it will in terms of VSG, it will be, let me write VGS small VGS equals to 4 millivolts, then small VSG equal to minus 4. It will be it is minus 2. That's 28 millisiemens into minus 4 millivolts. It will come out to be 112 microamps. Okay, and till the answer. Any doubts in this question? Please unmute yourself if you have any doubts in this question. Yes, Shivam, you have any doubt? Shivam, if you have any doubt, please unmute yourself and ask.
Hello, sir.
Hi, Shivam. Yeah.
Sir, how could we know that in this equation that which term is current source and which one is act as a resistor?
What do you mean? Where have I talked about
Uh,
resistor or current source?
the equation is written here: ID equals to del ID over del VGSG
Okay.
at operating point ID. So in this
Yeah.
equation, how can we understand that which one is current source and which one is a resistor?
Okay. So actually, what is resistor? R equal to V by I, right?
Yeah, sir.
But here it is I by V. I by V. This is inverse of a resistor. That is uh, conductance. It is conductance G, right?
Okay, sir.
And when we multiply that conductance by a voltage, then it becomes a current source.
Yeah, sir.
Is it clear?
Yeah, sir.
So how is it a current source? If you see, like, is it so? It is I by V into I. Sorry, into V. So V say we cancel, we get I. So this is how it acts as a current source. If you draw the small signal model, it was something like this, right?
Yes, sir.
Yes. Anything else? Okay. If not, let's move ahead to the second question. So in this question, In this question, we have a PMOS device just similar to the last question. Only this RD is added, right? So in PMOS, this is source, this is drain, this is gate. This drain resistance is added. K is same as before, VT is same as before. RD value is given, and we have to find the current ID. This is DC current, capital ID. So this is the total current. This is the sign convention. I subscript capital D is the total current equals to this is DC and this is small signal. Okay. They have taken the convention positive current flows from top of the page to the bottom of the page. So this direction current is positive. Okay. So we just have to find ID. So let us see how we will do that. So this is the same diagram and we have to find this I. We are given this resistance value RD. Okay. So what do we have? ID equals to K VSG VSG minus VTH whole square, right? ID equals to what is K? K is 28. Okay, let's write it as K only right now. And what is VSG? VS is 3.3 volts. VG is minus ID RD. So what is the voltage drop across this resistor? It is if ID current is flowing, the voltage drop is ID RD, right? So voltage at this node or voltage at the gate is ID RD, and VS VSG equals to VS minus VG equals to 3.3 minus ID RD. So that is what I am writing here, minus VTH. So this K 3.3 minus ID RD value, okay, I'll put later, minus 0.9 equals to K whole square. 2.4 minus ID RD square. So let us expand this. We will have to solve this quadratic equation. K 2.4 square plus ID square RD square minus 2 into 2.4, that is 4.8 ID RD, right? So if I just rearrange it, ID square RD square K minus ID 4.8 RD K plus 1 plus 2.4 square K equals to 0. Then I will need to solve this quadratic equation. RD value I can put as, how much is it? 3.76 kilo ohms. K is 28 millisiemens per volt. ID we have to find. So ID we will find by right. So if we solve this, we will get two values of ID. Since it is a quadratic equation, it will have two roots. ID will be, so I'll leave it to you to solve this. I will write the answers. 0.6 milliamps and 0.68 milliamps. So we will get two answers for ID. So which one is correct? So how to identify that? Okay. So to identify that, we will so to get a positive current, for this current to be positive, this thing under the bracket should be positive, right? So let's see, with this value, with both these values of ID, we'll get this as positive. when ID equals to 0.6 milliamps, 2.4 minus ID RD equals to 2.4 minus 68. Okay, let 0.6 to 3.76. So let me calculate what it is. It is 0.144. And now when ID equals to 0.68, then 2.4 minus 0.68 into 3.76. It comes out to be minus 0.156. So since this negative value is not accepted, we will have only answer ID equal to 0.6 milliamps. And let us see, yeah, we have it as the answer. Any doubts in this question? Please let me know if you have any doubts in this question. Okay, thanks, Shivam. Now let us move on to the next question. So now we have an NMOS, right? This is NMOS. And again, we will have to find, what do we have to find? We have to find the maximum value of RD for which the device is in saturation. Okay, right. And what is given? R2 and R1 values are given. R2 is 100 and R1 is 5.7 kilo ohms. And K value is given. Okay, so let us try to solve this. And VT is given 0.5. So here is the circuit and I have written all the values. It is 575.7 K. It is 100 K. RD we have to find. Okay. So first thing is we have to find the voltage here, VG, right? So this is a simple voltage divider. So VG will be 100K by 100K plus 575.7K into 5 volts. So VG will be 0.74 volts, right? Okay. Next is ID equals to K times VGS minus VTH whole square. It is K is 1.16 millisiemens per volt. VG we know, VS is ground, so VGS is 0.74, VTH is 0.5 whole square. It is 1.16 into 0.24 square. So it will come out to be 0. Okay, yeah, it is 0.068 668 milliamperes ID. Okay, now we have to find RD for which the device is in saturation, right? So let us apply the condition of saturation. For saturation, we know VDS, the drain to source voltage, this voltage should be greater than VGS minus VTH, right? So VDS should be greater than equal to VGS minus VTH. So if we just, okay, VD minus VS is greater than equal to VG minus Vs minus Vth. Let us cancel this Vs and Vs. Okay, now what is Vd? Okay, so this voltage here is Vd, right? So Vd is 5 minus Id Rd, because current Id is flowing through this branch, right? Id will flow from top to bottom. So the voltage drop here will be IDRD, and the voltage here will become 5 minus IDRD, because 5 volts is the supply here. So let us put this value 5 minus IDRD greater than equal to VG is 0.74, we just found out, and VTH is 0.5. So 5 minus IDRD is greater than equal to 0.24 minus IDRD is greater than equal to minus 4.76. If I put this 5 here, so it will become 0.24 minus 5, right? And it will be minus 4.76. So if we uh, multiply this by minus 1, then if we multiply this by minus 1, so this sign will change, right? IDRD is less than equal to 4.76. So RD should be less than equal to 4.76 by ID. It is 4.76 by, this is the ID, 0.0668. It will be kilo ohms because it is in milliamps, right? So I write here RD will come out to be, if I solve this, 71.2 kilo ohms. This is the maximum value. Since RD should be here, I've written it. RD should be less than this value. So I should write it like this, less than equal to. Yeah. So 71.2. So this is the closest we'll put this. Yeah. Any doubts in this question?
No, sir.
Okay. So should we move ahead?
Yes, sir. Yes, sir.
Thank you. Okay. So this is the next question, and here they are talking about this earlier circuit only. So this circuit here, here they're saying RD is 35.5 kilo ohms. They have taken. What is the maximum current ID that can flow through a device such that it is in saturation? And ignore the earlier values of R1 and R2. Okay. So let us try to solve this. It is a very good question. So now we don't know R1 and R2. We know RD is this much. We have to find maximum ID so that it is in saturation. Okay. So ID equals to K VGS minus VT whole square, right? And for saturation, we know VDS should be greater than equal to VGS minus VT. So we have to find ID. So what we will do is we'll put this instead of VGS minus VT, we will try to introduce ID somehow. ID here, right? Since we have to find ID, maximum ID. So we will find ID from here. So ID will be okay. So VGS minus VT equals to ID by K under root, right? So let us substitute this value here. VDS should be greater than equal to under root ID by K. And what is VDS? VDS equal to 5 minus ID RD. Since ID is still here, so VDS equal to 5 minus ID RD. 5 minus ID RD should be greater than equal to under root ID by K. And if we take square of here, 5 minus ID RD whole square is greater than equal to ID by K. So let me write this way. ID by K is less than equal to 25 plus ID square RD square minus to 10 ID RD. Right. So, okay, are we missing something? Yeah, yeah, fine. So ID is less than equal to again K times 25 plus ID square RD square minus 10 ID RD. So it is very similar to the previous question. We just have to again solve this quadratic equation. So our final equation that we have to solve is ID square RD square K minus ID 10K RD plus 1 plus K 25 equals to 0. So this is the equation that you have to solve. RD we know 35.5 kilo ohms, and K we also know 1.16. We have to find ID. So it will give us two values of ID. ID will be equal to 0.15 milliamps and 0.13 milliamps. Then again, we have to see if these both satisfy the our conditions or not, right? So what do we want here is that for saturation, VDS should be greater than VGS minus VT, right? So we will just see uh, this is if uh, if VDS is coming out positive or negative or what, right? VDS equals to 5 minus ID RD. 5 minus, let's say 0.15 into RD is 35.5K. So it will give me some negative value, whereas VD equals to 5 minus 0.13 into RD will give me some positive value. So the final answer will be 0.13 milliampere. So if you see in all the questions in your assignment, we just need to know these two equations. First is this saturation equation, and second is the current equation. And with this, with just modifying these two and substituting some values here and there, you can always solve any question. And yeah, okay. So it is 0.13 milliampere. So in microamperes, it will be 130 micro, right? So this is the answer. Any doubts in this?
No, sir.
Okay. Next question. Again, consider the earlier circuit with R1, R2 values from Q3, RD values from Q4. Due to temperature and some other imperfections, the K is no longer the stated value in Q3. Okay, so we had stated earlier it was 1.16, now it is 2 times of that. 2 into 1.16, that is, sorry, 2.32 millisinus per V. This is the new K. and they're asking will the device be in saturation. Okay, let us find it. So let me see. Okay, so this is the circuit as previous. R1 and R2 values are previous values. RD value is just 35.5. They have shown RD value from question 4, R1, R2 values from question 3. K is 1. Earlier it was 1.16, so 2K now is 2.32. And VG, we have already solved this earlier. It was VG is what? R2 by R1 plus R2 into 5. So it will be 0.74 volts. So if we try to solve it, ID equals to 2K. So I'm writing 2K. Okay, so equation is actually K VGS minus VTH, right? But now they are saying earlier K has changed to 2K. So I'm using this new value. So it will be 2.32 millisiemen per volt. VG is 0.74 and VS is 0 minus VTH is 0.5. So this will give me ID. So ID is 0.133 0.134 milliamperes. So when we solve this, we will get ID equals to 0.134 milliamperes. And okay, so next is what do we have to find? We have to find what is the region of operation is. Okay. So for that, for saturation, we know VDS is greater than equal to VGS minus VTH. Or for linear, it is VDS is less than equal to V. Okay, not equals to less than VGS minus VTH. Right? This is saturation. This is linear. So in any case, we need to find VDS, right? So VDS equals to, let us see, VD equals to VDS because VS is 0. So VD equals to VDS equals to VDD, okay, not VDD, let's say 5 minus ID RD equals to 5 minus 0.134 into RD is 35.5. So it will come out to be 0.24 volts VD. So let us see the equation VDS 0.24 VGS minus VTH. We already know it is 0.74 minus 0.5. It is also 0.24. So now what we have is VDS equal to VGS minus VTH. So this is edge of saturation. Right. So answer is it will be at the edge of saturation. Any doubts in this question?
No doubt. I just wanted to add, if we add an resistor across load resistor across D, so
Yeah.
then can we use the same current equation, ID equal to K into VGS minus VT the whole square?
Uh, yes. Yes. This equation will hold because so this equation is valid for only these three terminals of MOSFET: gate, drain, and source. We are adding RD over the drain, or we are adding load over the drain, right?
Yes.
So
Yes.
this ID equation will be valid. We are Since we are only considered with this GS and DS terminals. So the same current ID will flow, but the equation that I put here, like this equation, this might change. This is
Yes.
because this is simple case KVL, right? So if I add
Yes.
another branch here, this equation will change. It will not remain same. It will be 5 minus RD minus, let's say, whatever current it is. I don't know if it will not be ID for sure. ID,
Yes.
because ID will be here only.
Yes. Yeah, it
So
will
if I
split
add
up. I
another branch, yeah.
dash. Yeah.
So it will be, let's say, I1 RD plus I2 RL. It
Yeah.
will be something like this.
Okay. But we can use the same current formula. ID
Yeah,
equal
current,
to,
this won't change. Yes.
yeah, only the value of VD will change.
Yes. Anything else?
So basically, the ID would be the current which flows from the VDD. So that
No.
remains the same, and it will split into I1 and I2. Okay, got it.
Yes. Yeah.
Correct, na? Correct, na? Okay. So it will basically like ID is equal to I1 plus I2. Okay.
Yes. Yeah.
Right. Yeah, thanks, thanks, thanks.
Any other question? Anybody else? Okay. No. Fine. Let us move on to the next question. Yeah.
Can
Yeah.
you just check if there is any AC coupling for these circuits? If anything in
In
the
this,
next, no anything later on also. Just show one example of AC coupling.
yeah. Yeah. I'm
Yeah,
getting to that.
sure, sure.
So
Thank you.
actually, in this assignment, we explicitly do not have any AC question. Let me see. Okay. So they have
Yeah,
shown,
we
try
have.
to show this here. So I'll solve this one. Okay.
Okay, fine.
Just how much time do we have left? We have 40 minutes. Yeah, I'll solve this one. Because this question, it requires me to solve this question 6 first. So I'll solve this first, then we'll go to that question.
Yeah,
Okay.
please, please, please.
So in this question, what is different is they have now added a source resistance RS, right? So we are given R1, R2, RS, and RD. All these resistance values are given. And what do we have to find? We just have to find ID. So it is a simple question. So let's just solve it quickly. So this is the circuit, and I have written all the current values. ID will flow like this. So again, if we solve VG equals to 327K by 654K plus 327K into 5, it will be 1.67 volts. Now simply applying the current equation, K VGS minus VT whole square. K is given, fine. What is VG? VG we know, 1.67. Now Vs is not 0 this time, right? So instead of Vs, I will have to write minus IDRS, because the drop here will be IDRS, right? So VGS will be VG minus Vs equal to 0. I'm sorry, let me just write it here. VGS equal to VG minus Vs. VG is 1.67 minus Vs is IDRS. So I'll just put this here, minus VT whole square. So again, uh, okay, let me solve it a little bit further. K equal to 1.17 minus IDRS. I'll just write it finally. By solving this quadratic equation, we will get two values of ID, 56 microamps and 47 microamps. So if we take this higher value, 56 or 56 microamps, Vs, our VGS would become negative. So this value won't work. So ID will be 47 microamps. So now uh, I'm moving a little bit faster because this is like very repetitive, and we have done this analysis already in previous questions. So if there is Any doubt here, please ask.
Is it 4.7 or 47 micron, sir?
Sorry,
Is it 4.7 or 47 micron?
I think it is 47. Uh, have you solved it to be 4.7? Hello, Bhuvnesh.
Sir,
Yes.
no, I just got 4.7 only there.
Okay, just I don't know. Recheck the values and okay. We will come to it at the end if there is some mistake in the value. But currently, I was getting 47, so I've written it. Is there any other conceptual doubt in this apart from calculation mistake?
Sir, I have a question.
Yes.
Like, why we use register in order of k
Sorry.
input? Sir, why we use register in order of k? Like, we can use simple register in ohm without taking in k ohm.
Okay. Yeah. So it is a good question. So maybe I think in future lectures you will see these resistance values are they determine the stability of the circuit and also the gain of the circuit. So gain is actually equals to AV equals to GM times R out. So we want our circuit to have very high output impedance, and if it is a voltage amplifier, very high input impedance also. So if both input and output impedances are very high, it will be a good voltage amplifier. So it actually depends on use. So yeah,
Okay, okay. Thank you, sir.
so it will actually depend on the application where the circuit is being used, but these high values of resistors help in the stability.
Okay, thank you, sir.
Okay. Yeah. I think this will come ahead in this course. So it will be more clear then. Should I move ahead to the next question?
Sure, sir.
Thank you. So this is again in the earlier circuit, compute GM. So this is very simple. Okay. Let us see. Okay. So we know GM equal to del ID by del VGS equals to so ID what we have K VGS minus VTH whole square. So del ID by del VGS will be 2K VGS minus VTH. It will be 2K was K was 4.7 milli. Sorry, 2 into 4.7 millisiemens. VGS we had solved 1.67 minus IDRS. 1.67 minus IDRS minus VT is 0.5 whole square. Oh, sorry, not square here. This is not current. So 2 into 4.7, it will be 1.67. IDRS, if you do 47 mu into RS, will be 22.7K minus 0.5. So this will come out to be 0.94 millisiemens. Yeah. So that is 940 microsiemens. So this is the answer. So this is very straightforward, and we are just using previous values here and just putting it in a formula. So there is uh, nothing that conceptual here. So let us move on to the next question. We have less time, but let us solve this one. We will solve this. Okay. So what do we have to find? We have to find the small signal gain of the circuit. We are applying input here and we are taking output here, right? And it is small signal gain. And the capacitors are so large that they behave as short circuit for time varying signals or small signals. And assume that the MOS device characteristics are perfectly flat in saturation region. So this is a very important line. What it means is, so if this is our MOS device characteristics, so let's say this is this is ID-VD graph. So it looks something like this, right? So here earlier it is in linear and here it is in saturation. So they are saying in saturation it is completely flat. So that means there is no change with VD in ID, right? So that means del ID by del VD equals to 0. And this is actually GD, right? GD equals to 0, output conductance. So I hope this is clear. If not, please speak up. And what is else is given? All resistor values are the same as earlier, and there is no dependence on VDS whatsoever. Yeah, the same thing is given. So let us solve this. Let me add a page. So
Sir, I have a question.
yes,
Is GD is related to channel length modulation?
yes, it is.
Sir, how?
Okay. So when we know, like, when we go to, if you have done any short, any devices course, like this is the MOSFET, right? So when we, let me just write it here only. So if this is, let's suppose this is my IDVD curve, right? This green one. So do you know what is early voltage? So early voltage is when we extend it, where this comes out to be when the current is 0. So we call it early voltage, VA. So due to channel length modulation, ID becomes K VGS minus VTH whole square into 1 plus lambda VDS, right? So you might have seen it somewhere if you have done any devices course. So this
Yes.
lambda is nothing but 1 by VA. So what is happening in channel length modulation is that earlier our current was independent of the drain voltage, right? We were assuming that our current is flat, totally flat. There is no change with VD. But now when we consider this, our current becomes dependent of VD. So yeah, this factor uh, signifies that. Is it clear?
Yes, sir. Yes.
Okay. So now if I do del ID by del, oh sorry, del ID by del VDS, it will not be 0, right? It will have some value. So GD output conductance will not be 0, and it is like obvious from the fact that this has some slope. It is not 0. So GD is just slope of this, right? So if the slope is 0, GD is 0. If it has some slope, then it is not 0. So for this case particularly, the early voltage VA is infinite. So if we extend it, it will never meet this VD. It will keep on going till infinity. But if it does have some slope, it will somewhere meet uh, this x-axis and will give us the value of VA. Okay. Uh, so let us go ahead with the question. Okay. So what do we have here is this. R1, R2, RD, RS. They're taking V out here, and V in is given here. Right? These are both small signals. It is 5 volts, let's say. This is ground. Okay. So they are saying that why I have not drawn any capacitors, because they have stated uh, they act as short circuit for time varying signals. So that is why I have not drawn the capacitances. So to do the small signal analysis, what do we do? Our first step is change any voltage source to DC voltage source to short, uh, source to ground. So this 5 volts will change to ground. So why this is happening is, so we are what is small signal actually? So let's say if this is a DC voltage, let's say VD flowing through some wire. So what is a small signal? We apply a very small time over it. That is small VD. It's a small signal that is applied to the existing DC signal. But for batteries or voltage sources, since this point is fixed by a battery, I have connected a battery here, right? So this battery will not allow any change to happen here, because if this is an ideal battery, it will always have plus 5 volts maintained here. It will not go to 5.01 or 4.99, right? That is why it changes to, for the small signal analysis, we changes to ground. So I hope it is clear. If not, please ask me. So let's move ahead. So the small signal current ID will be flowing here, right? Okay. So if we solve this again, I'll write the previous equation. ID equals to GM VGS plus GD VDS. So this called the universal equation, and it can solve any question of small signals for MOSFETs. So I recommend you to learn it by, and with this any question of small signal analysis you can easily do, right? And we have seen where it comes from, right? In the first question I had shown, uh, yeah, it comes from here. So this is GM, this is GD, GM VGS and GD VDS. This is GM VGS GD VDS. Okay, let's go back. So here, yeah. Yeah. So since they have already said, we have already found out, right? GD is 0.
Sir, I have a
So
doubt.
we will use, yes,
Excuse me, sir. I have a doubt.
yes.
RS gets short circuited, sir, because of this capacitance.
RS gets
RS,
short circuited?
yes.
No.
See, so we have capacitor across the
Oh
source
yeah,
resistance RS in the small
yeah,
signal
right,
equivalent.
right. Yes, you're right.
Okay, okay, sir.
RS will get short circuited. So, okay. So, okay, we know GD is 0. We had just seen the characteristics. So ID will be GM VGS only. So one more thing we have to find now is V out, right? So what do we actually have to find? We have to find the small signal gain. So gain will be V out by V in. So we somehow have to introduce V out in this equation to get V out by V in, right? So what is V out? V out is 0 minus ID RD, right? So if I apply KVL here, 0 minus ID RD is V out. So if I substitute this ID equals to minus V out by RD minus V out by RD equals to GM VGS. So V out by V in equals to minus GM RD. And GM we had calculated, I think it was 940 microsieverts minus 940 micro, and RD was 22.7 K. It will come out to be minus 21.3 volts per volt. Yeah. So now I think Pawan had asked, right? So here why we want to have a high RD.
Yes,
So is this question clear?
I got it. Yes.
Anybody else has any doubt in this question?
So if there is a 1 volt, then it will be multiplied with 21.3. So we will get output as 21.3 volts.
Yes, yeah. So actually we will not have, because okay. So
Yeah,
small
I got it.
signal means, yeah.
It's 5 volt at the input, so it gets saturated.
Yeah, right. But typically we apply very small signals. So if we have, like, let's say if your
In
here it
millivolts.
is 5 volts,
Yeah.
your, yeah, it should be in millivolts or less. Yeah.
Yes, got it.
Because if it is higher, our circuit is not linear anymore. So it will give, so our V out and our V out and V in relationship will not be linear. V out will not directly depend on V in. So it will have some quadratic or some other terms which are unwanted. So to maintain that linearity, we always keep it as small signals here.
Why did we consider GD to be 0? GD as 0? Uh,
Okay. They had given in the question, right? So
okay.
the characteristics are in saturation is flat.
Okay,
So I
fine.
had shown this, right? So if this
Yes,
is flat, there is no
there is no slope.
change. Yeah. So GD is 0.
Got it.
Sir, I have a doubt, sir.
Yes.
Sir, how to answer this question? What is a small signal? What is the better way of defining this small signal?
Okay. So what a small signal is simply, uh, let's say you have biased your circuit somewhere. So you know what biasing means. Let's say earlier what we were getting, right? It was 1.67 volts of VG here, right?
Yes, sir. Yes.
So this was, let's say, 1.67. So what you did was, so what this biasing will do? So this biasing will just put it in saturation, right? Because VGS is greater than VTH, and let's say VD is also greater than VGS minus VTH. So it will put in saturation. But what your small signal will do, you will superimpose it on 1.67 itself. So it will go to, let's say, 1.6, let's say 1.68 or 1.65, something like this. Very small value will change here. So with this small perturbation, what will be the perturbation at this node? So I don't know. Have I confused you more?
Okay, sir. Understood, sir. Understood.
So the large signals are basically used for biasing, and the small signals are what we actually want to amplify. So these small signals are typically coming from, let's say, some sensors that are here, right? These sensors will output very small voltages in millivolts or microvolts, and we want to actually amplify these signals to use them, to detect them, and to do something with those sense signals. So that is why uh, we apply these small signals in MOSFETs to get an amplified version.
Okay, sir. Understood, sir. Understood. Thank you, sir.
So there is a mathematical formulation of small signals also. So small signal, uh, small signal should be less than equal to, I think, 2 times VOV, or should be much less than this. So it comes out if you solve the current equation and do some approximations. It comes something like this. But yeah, this is not important. I'm just telling you. So VOV is just overdrive voltage, that is VGS minus VTH. So it should be much smaller than two times overdrive voltage, two times of VGS minus VTH. If we mathematically try to solve how small should be our signal to get linear V out equal to A gain times V in. For this to maintain this linearity, our small signal should be smaller than this. Uh, so this is not important, and this mathematical formulation, but for what is small signal, I'll recommend you to rewatch the video. I think Sir has explained uh, what small signals are and why we are concerned with them. If not,
Oh,
please feel free to write to me.
yes, sir. Okay, sir. Understood, sir. Understood.
Okay.
Thank you, sir.
So yeah. So it is 4 p.m. already, and let me just tell you the next question very quickly.
Sir, I have a question.
Yes.
Sir, if we are considering the channel and modulation, and we are considering that GD is not equal to zero, then what will be
Yes.
the scenario?
Then okay. Right. So then this term will not be zero, obviously. Yeah. And here, what will our VDS will be? VDS will actually be V out, right? Hello, Venkat.
Sir,
Yeah. So
following, sir. Following.
yeah. So our equation will become something like ID equal to GM VGS. So let me write it like this: GM V in plus GD V out. So if I just replace this here equal to minus V out by RD, I can still solve it linearly. I will get V out by V in, right? So just some mathematical formulation will change, but you can still get V out by V. It won't matter if GD is zero or not.
Okay, sir. Thank you, sir.
But conceptually, we want uh, GD to be as low as possible. So what happens is if we have this GD, what will happen is our gain will become AV will become minus GM RD parallel with uh, 1 by GD. So if let's say GD is not zero, it has some high value, let's say 10k ohm or something like that. So this RD parallel GD will become small, right? So our gain will reduce. That is why we want GD to be zero or as high or as low as possible. Is it clear?
Yes, sir. Yes, sir.
Yes, sir.
Okay. So the next question, I won't solve it, but it is very similar to what we had done in one of the previous parts. We just have RS here extra. So we just have to find the maximum RD for which the device remains in saturation. So it is very easy. I'll just quickly write. So if I apply KVL here, 5 minus IDRD uh, minus VDS, if with the voltage here is VDS, minus ID RS equals to 0. So if I just rearrange for RD, it will become 5 by ID minus VDS by ID minus RS. So here ID we know it was 47 mu, and VDS we had solved in one of the questions, it was 0.1 volts where he had solved it. Let me show you. Uh, Okay, where we had solved VDS. Do you remember where we had solved VDS? Uh, okay, yeah, here we had solved it.
Number
I
five.
think.
Question number 5.
Okay, not this one. So here, when we were solving this, we had found out that VGS equal to 1.67 minus IDRS, right? So when we solve this IDRS, uh, it will be 1.67. Okay, leave it. I don't remember where, but whatever you can substitute this value. I don't remember what this value was exactly, but please find out from the previous questions. I'll upload the slides, and you can simply find RD just by substituting these values. This is 22.7K. So this is straightforward question, and RD should probably come out to be 81.5 kilo ohms. And the next question is again similar to the previous question. Here, everything is given. They just have changed K to 2K. So it is very similar to, I think, question 6. It is same as question 6, just K is changed to 2K. So in question 6, yeah, we had find this ID. So it will change to 2K and this ID. And if you, by changing this to 2K, if you solve this ID, you will get something different. So see that. Okay. So the answer to this one should be this 48.23. So please try to solve these both. I have skipped a lot of details in the last two questions, but they are very straightforward and similar to what we had done earlier. Okay. And if you have any doubts, please, you can email me. And this is my email ID. I'll share. Yeah, this is the email ID. If you have any doubts, please write to me. And if you don't have anything to ask, we will close the session. So please let me know if you have any doubts.
So what is the specific book we can refer for solving problem?
For solving problems, you can refer to uh, Behzad Razavi. I'll write in chat. Okay, let's go. Razavi is a
Micro,
very good book. Yeah,
yeah,
microelectronic
micro
circuits by, yeah, by Razavi, and it's a very good book for analog circuits. I think it is called, yeah, microelectronics, and I don't remember the complete name, but it is microelectronics. Yeah. So you can refer to this book if you want to practice. Anything else?
No, sir. No, sir. Everything clear.
Okay. So
Thank you, sir.
thank you
Thank you
all.
very much.
Yeah,
Yeah,
thank you.
1 minute.
Yeah,
Sorry.
hi.
You mentioned some output impedance should be, sorry, high input impedance and high output impedance. Isn't it
So
not
yeah,
the high input impedance and low output impedance?
yeah. So it is for transconductance amplifier. So for transconductance amplifier, I think it is should be high and high, right?
Transconductance, okay, it is
So
I by V, I by V.
yeah. So if we apply a voltage input and we have output as current,
Yes.
so for this it should be high and high.
Okay.
But yeah, you're right. I think for voltage and voltage it should be high and low.
High and low. Okay, fine.
Yeah.
So, but just one thing. For anything, for any of the applications, we'll get both V and I, right?
Uh, Actually, we don't. So uh, let's say for this particular case,
Yes.
for V and I, So VN and ID. This use a simple common source amplifier. So common source amplifier is nothing, just what we had seen earlier, just a simple NMOS
Yes,
is
correct.
common source amplifier. But so what we have in common source amplifier is we apply input at gate and output at drain. So, but
Yes.
actually this output we prefer to take ID because this V out, because since this is a high impedance node, we do not prefer to take V out from here because for V out we need low output impedance, right? So what do? Is we connect a buffer after
Yeah.
this.
Mhm.
So buffer is actually a common drain amplifier. So this you probably will see in upcoming sessions. So
Got it.
common drain amplifier will have very low output impedance, but high
Input impedance.
input
Okay.
impedance. So it will kind of act as a matching circuit. So it will match with output of this
Yeah, it's
and
like a
give us
common
yeah
source follower.
yeah. And it has gain also of just around 1 volts or 0.9 something
Okay.
like this. So it is very often used like this to make a voltage amplifier. But yeah, we can get a V out here. That's true, but we don't prefer it because of
No,
the
I
impedance.
so this is being the high impedance or the low impedance is being done because of sorry, we it's based on the configurations of the MOSFETs.
So it
Which one we
actually,
need to?
yeah. So it actually depends also yeah, on the configuration, but actually on drain we always have GD, which is generally sorry, the impedance here is we minimum have 1 by GD, which is generally very high because GD is usually low for good transistors. So we mostly have high impedance, but the source terminal has very low impedance.
Okay. Hmm.
So it actually how to find these impedances is simple. So let's say this is gate drain source. So let's suppose I want to find the impedance at drain. So what will I do? I will just connect a test source, let's say V, and send a test current, let's say I, and when I will ground both the others. And I'll just apply this
It's V by I.
ID,
Yeah.
ID equal to, yeah. So impedance here will be V by I. So I'll just apply the universal equation again here. ID equal to G
Yeah,
VGS
VGS plus.
GD
Yeah. Yeah.
VDS.
Yeah.
So if I solve this, I'll get some formulation like ID will be, oh sorry, I by V will be 1 by GD or something like that.
Okay.
So if we do for source, I think we get 1 by GM, uh, something like that. I'm not exactly sure, but yeah, we do some approximations. We get 1 by GM from if we check the impedance of the source. So GM is generally high, so the impedance here is low. And that is actually the concept of the common drain amplifier. Here we take output at the source node.
Yes. Okay. I'll go through the I'll go through. I have this one, not from Razavi, from Millman. I'll
Okay,
just walk
yeah,
through that. I'll,
okay,
I'll maybe next time I'll just check the book.
sure, yeah,
Thanks, Om.
thank you. Okay, so now we will end this session, and if you have any doubts, please do email me. Okay. Thank you all.
Thank you, sir.
Thank you. Thank
Thank
you.
you.